Hi, folks. We're going to get started in just a couple seconds here. Thank you. All right. Hi, good afternoon, everyone. Thank you so much for joining us. My name is Meta Polywall with the Orange County Water District, and I'm very excited to welcome you to our webinar today, all about the opportunities of using artificial intelligence and application tools and applications in the water sector. Let's see. So before we begin, I do want to mention that we are in webinar mode, so attendees are muted to reduce background noise. The webinar is being recorded and will be available on the OCWD website and YouTube channel. And lastly, we'll take questions at the end of our presentation, so we do encourage you to use that Q&A box located at the bottom of your screen to ask questions today. And we will do our absolute best to get to as many questions as possible and address questions most relevant to the information presented today. In the event that we're not able to get to your question to the time frame allotted, we are absolutely happy to follow up with you after the webinar. So please do include your contact information or ask that question associated with your email address so we can get back to you after. And without further ado, I'd love to introduce our speakers today. Dr. Megan Plumlee is the Director of Research for the Orange County Water District, where she oversees a team of research scientists and engineers conducting applied studies to support the district's core operational needs. This includes evaluations of promising new technologies for the advanced purification process for potable reuse, as well as for groundwater recharge. And Dr. Plumlee has authored or co-authored over 40 peer-reviewed publications in scientific journals. The next up will be Dr. Kate Newhart. Dr. Kate Newhart is an assistant professor of environmental engineering with a specialization in data-driven monitoring and control for the water sector. She holds a Ph.D. in civil and environmental engineering from the Colorado School of Mines and previously worked at Metro Water Recovery in their technology and innovation division, where she led data handling and data-driven modeling efforts. Dr. Newhart's current work includes soft sensor development for disinfection, resource recovery, and DPP mitigation in collaboration with utilities and universities across North America. And Dr. Kyle Thompson will be closing us off. Dr. Kyle Thompson is a national PFAS lead and a reuse lead technologist at Carollo Engineers. And his areas of expertise include PFAS, potable reuse, and machine learning. He received his Bachelor of Science in Environmental Engineering from Missouri University of Science and Technology, and a Master of Science in Civil Engineering and Ph.D. in Environmental Engineering from the University of Colorado Boulder. He has a professional certificate in data science from Harvard and is a registered professional engineer in the state of Nevada. Previously, Dr. Thompson worked as postdoctoral researcher at the Southern Nevada Water Authority. So with that, I'd love for us to get started, and I will hand it over to Megan. Megan, please take it away.
All right, thank you so much for that introduction. Hopefully everybody can see us and hear us okay. So I'm just going to give a very brief introduction before turning it over to Kate and then Kyle. So first, just a quick introduction to who we are at Orange County Water District for those of you that may not know us yet. So we serve an area of North and Central Orange County in Southern California, and we essentially function as a groundwater wholesaler. So we manage this really important drinking water supply here that is the groundwater system. This groundwater provides 85% of the drinking water here. So we're really proud of, have this resource and the management of it, and lucky to have it. But to keep up with the incredible demand for water, we have to do some active interventions in a very big way to basically augment this supply. And so to do so, we do recharge. So we have lots of land and recharge basins where we let gravity do the work of percolating water supplies into the ground. So we divert certain water supplies into these spreading ponds and do the recharge. And as part of that water supply portfolio, we do recycle. We include recycled water. So that's the groundwater replenishment system, or GWRS, where we take water that would be disposed of, essentially wastewater, that would otherwise be disposed of, and we advance purify it to recycle it as a drinking water supply to include in our sources of water for the recharge operations. So that's OCWD in a nutshell. Next slide, please. So we've been really intrigued by all the recent activity and interests and buzz around artificial intelligence, specifically in the water sector. We're asking ourselves, could AI really help us make better decisions? I think with the introduction I just gave of our facilities, you can see that, this is pretty complex, right? Operating all these facilities, the technology itself, the equipment, but also just overall as an organization, we're multiple groups of different people working together in different departments. We've largely moved away from paper and have, digitalized, right? But there's, different data sets, various data sets. There's lots of information there. Maybe we're only using kind of the surface of it to make decisions. Perhaps there could be more richness and interpretation of that data with more advanced methods. Overall, it's just a lot of moving parts, figuratively and literally. And so the idea is, could artificial intelligence and machine learning tools help people, enhance efficiency of the workplace, enhance our operations, maybe reduce energy, reduce chemical use, that sort of thing, really, and just get more access to information for staff. Next slide. So at OCWD, we have a history of innovation. We like to say innovation is in our DNA, it's who we are. So we're definitely open to testing these new ideas around AI and machine learning, but it needs to be economical. It needs to have sort of a tangible or practical way that it'll help us improve operations or reduce cost. And so I would say we're now like dipping our toes into this through some studies. And so at this time, we have launched about 4 projects in the AI space that I would categorize as either research projects or like product testing, where we're looking at certain commercially available technologies in the AI space that we're basically giving them a try, so like piloting the technologies. And these projects are either just getting started or maybe only about halfway through. So we decided not to present that work today, because then it might not be as satisfying if you see an introduction but don't get to hear the results yet. So stay tuned for maybe a future webinar talking about the outcome of all these projects. So today, instead, we decided to really, set the stage. Next slide. So today's webinar is more of an introduction to AI in the water industry. Kate's going to give us Artificial Intelligence 101, and then Kyle will talk about some applications. So with that, thanks again for attending today, and I'll turn it over to Kate.
All right, well, thank you all for having me today. Hopefully in about the next 15 minutes, I can introduce what is AI and ML, how can it be used in water sector operations, what are the big misconceptions, and a few of my final closing thoughts after spending the last many years working on this project, both at a utility and in the academic sphere. So to kind of understand what artificial intelligence is for the current day, I like to kind of tell a little bit of history. So it's 1956, a group of mathematicians and early computer scientists get together at Dartmouth College, and they are building algorithms which can learn, right? Something that we normally attribute to needing human intelligence to execute. However, right, 1950s, 1960s, the math of what we know as our modern day AI has been developed, but it's lacking the computing power to really leverage and understand what these algorithms can do. So it isn't until the 21st century, we have our big computing boom, and now on a standard issue work laptop, you can build all of these AI algorithms. So you're seeing this boom in AI research across all sectors, and the water sector is no different. So if we look at the modern day definition of AI, AI is a computer system that can perform tasks that we typically associate with requiring human intelligence, right? So all those CAPTCHAs, those images that you have to solve, those are getting more and more difficult because we have more and more training data for the algorithms right, for our artificial intelligence. Tesla's object detection, right? Whether it's detecting cars or people, there's a host of different ways that AI is already influencing your day-to-day life. But one of the things that I think is frequently overlooked in this definition and the conversation around AI writ large is that AI is mimicking human intelligence, right? It is mimicking learning. It is simulating human decision-making, but it isn't actually going through the individual steps that you go through to make a decision. Or if we're talking about an environmental system, it's not actually learning the law of gravity, right? Or chemical equilibrium. Rather, it's looking at the correlations between inputs and outputs and trying to find similar examples in its training data set, right? What does the car look like before it, right? Or in the caption, what does the V look like? So I think it's really important not to anthropomorphize, effectively what's just math from the 60s and modern day computing. So that's a little bit about what AI is and what it's not. But AI is actually a really, really broad field, right? So if you think of ChatGPT, that falls under the category of natural language processing. The Tesla object detection, that falls into the category of computer vision. And what my work focuses on and what we're going to be presenting today is the category of machine learning. So ML is an algorithm that can infer how to do a specific task without being explicitly told how to do that task. And we more often than not do what's called supervised learning, which just means that I have an explicit set of outputs that I'm telling the computer that I want it to mimic. So if you've done linear regression, you have done supervised learning. And it's just because, right, you defined your Y variable, you defined your model output, and you gave it specific examples. So that is what supervised learning is. The machine learning portion of that is that you may have said, I want it to be linear, but you didn't draw the line, right? You didn't give it the exact parameters. Instead, an algorithm went and iterated through until it found the line of best fit. So that is the machine learning component of this linear regression example. So let's extend this example a little bit further to understand how we train these machine learning algorithms. So in a model training process for a standard linear model, right, you have some data, you feed that data into a machine, right? Usually our machine is Microsoft Excel, right, in the water sector. And we say, okay, model, take on the form of a linear structure. And that linear model has two parameters, right? Slope and intercept. And as I just described, it goes through and it iterates until it finds the line of best fit. This is really similar to what's done in machine learning, except now we have a lot more data and a lot of different data, right? Maybe it's collected at different times. Maybe some of it is lab data, some of it's instrumentation data, some of it might be maintenance data, right? There's a lot of different data sources and structures. So to deal with all of that heterogeneity, we need to move outside of Excel, right? So that's why you see Python and R or other programming languages being the primary tool of machine learning modelers. And now the other side of the coin is that our model, it now doesn't have just two parameters. Now we're on the order of hundreds of thousands of parameters just for a simple model. So what I have shown here is what's called a neural network. Even a small neural network like this will still have a few hundred model parameters. So you better have a data set that has more than a few hundred, rows or observations. If you want to build a good model, right? But there are some similarities. So now let's talk a little bit more about what the differences are between what you may know as traditional modeling and where machine learning can play a role. So to do that, let's do an example. Let's say you have you have to apply some chemical, right? And this chemical is very expensive. So you want to do some sort of real-time dose control for that chemical. Well, maybe you go into the lab and you have some data, you look at the relationship and it's fairly linear, right? You fit the model, great. We classify that as a statistical model, right? Whether it's a linear relationship or really any of the variants of it that you find in the built-in Excel modeling features. But say maybe you see some nonlinear behavior, right? And you, as an environmental scientist, know that's likely related to pH, right? Or some other water quality parameter. And you know how that is related to maybe your dose, right? Or could affect it. So you can incorporate some physics, chemistry. We classify all of this as mechanistic information. So now we're fitting a mechanistic model, right, that has all of our prior knowledge incorporated into it. And that model has specific properties as well. But maybe even after we tried the statistical models and the mechanistic models, the error in our predictive model still isn't good enough, right? So the image on the right-hand side of your screen there shows that that red line, our model, it generally captures the shape of our data. However, if I'm talking about dose control, I need it to be really precise. And maybe this model still isn't precise enough to beat out how we're currently dosing this expensive chemical. So this is where machine learning might be able to come in, because I'm not concerned about which variables are doing what. I just need that level of precision. So I take maybe 10 other water quality variables, sensors that are just running, that I can collect that historical information from. Maybe I know how it's related, or I'm not quite sure how it could be. But the beauty of machine learning is that it looks for correlations. So maybe some of these other variables also vary, right? In the same way that we see the variability in this plot. So we fit our, what's kind of called generically as a black box model, and that's our machine learning model that we fit. So hopefully that gives us the precision that we need. But it's not just precision that we're looking for, right? When we fit these three different types of models, there are other consequences as to why we would choose one of these methods over another. So if we think about a simple statistical model, right, we explicitly define the relationships or the trends between variables. And in doing this, in some of the assumptions under our data, we get these analytical uncertainty estimates. That is just a fancy phrase for confidence interval, right? So statistical methods have that as an advantage. Mechanistic models, the relationships have physical meaning, right? And that can be really important if I'm taking rate constants, right? Decay constants, or if I want to compare two systems, right? So mechanistic models and statistical models have their time in place when you want to understand the system. Because once you get to machine learning modeling, what's going on the inside has no physical meaning. Those hundreds of coefficients inside the models are not related to in the same way, right, that statistical and mechanistic models are to the output. So now we're really looking at this really flexible model, but it's going to have to answer a different set of questions than statistical and mechanistic models have traditionally been able to answer for the water sector. So in what ways can these really flexible algorithms be used? Short list here. My favorite is what's called a soft sensor. So if you think of like a standard pH sensor as a hardware sensor, a software sensor is just a model, right, of maybe something that's really difficult to measure. It couldn't just be difficult. Maybe it's just time consuming, right? Maybe the analyzer itself is far too expensive for a utility to purchase and maintain. So soft sensors can be really beneficial and easy ways that you can plug and play with your existing control strategy and integrate a machine learning model. Alternatively, you can do things like early warning systems. So think of trying to detect faults either in a single piece of equipment or maybe in a process writ large, trying to see if things have changed significantly from other points in time. You can also do flow and load forecasting, right? Which is just a fancy version of prediction. And maybe that forecast can help your operators better respond, right? Or if you have an existing control strategy for that, can just be plugged right in. And then there is the phrase digital twin, which I'm sure you've all heard of. And I think this is my favorite definition of a digital twin specific for the water sector. So a digital twin is a model of a physical entity. So in the example here, I use a blower that has a bidirectional data connection. So it is both sending data and receiving some information. And that allows for dynamic updating of our model, right? So the model doesn't need to have machine learning, right? It could be just a mechanistic model. Maybe the machine learning component of it just handles a little bit of non-ideal behavior. And that's really popular, these hybrid model approaches, because that gives you the stability and the backbone of a mechanistic model and capturing the variation or the error, the non-linear behavior in an artificial intelligence or machine learning model. But it's really that this model is updating over time. So those are the three main properties of what we call a digital twin. The benefits of this could be, I could look for the most energy efficient set points, right? Or maybe I just want to see, maybe my blower is behaving abnormally, right? Outside of what it should be behaving, and I can trigger a maintenance activity to be done with the digital twin. So this is just an example for something small. It could be a much larger process, right? But this is what a digital twin kind of means under the hood. So it's always important that if you hear someone saying, you know, I have a digital twin or I can do this, it just has these properties, but there's a ton of different ways that this could be applied even within, you know, many different organizations. So how do you start your first machine learning project? Well, here is the generic machine learning workflow. Right. So I'm not going to, we could do a whole another hour or two lecture just on each of these individual you know, stages, but your role likely is going to be in defining the problem, because that's going to be the piece that's going to impact the rest of this cycle. And the rest of the cycle is going to rely on operations, lab staff, engineers, scientists, and data scientists, right, as a part of a team to be able to deploy and continue to maintain machine learning models inside of an organization. So I want to go over just three big myths that I have heard in my work in AI. And first off is, oh, I have a ton of data. That means I should use AI. If I had a nickel for every time I heard this, right? Well, unfortunately, we are not the Googles of the world. And the water sector is actually dealing with much smaller data sets than you would think. So while we don't have volume necessarily as the biggest problem, we have a lot of other problems that are specific to our data structures. And that's why I'm a really big advocate of having subject matter experts, right? Environmental scientists and engineers putting on the hat of data scientists, kind of like myself, in order to really understand the implications, right? Think of that cycle. At every single step, there's another place for a subject matter expert to inform the data-driven modeling process. So it's important to understand, just because you have data shouldn't mean that you use AI, because this mentality really is a hammer looking for a nail, right? If you have a problem, AI may or may not be the best solution. And it's important to really be specific with your problem statement and your objective before you dive in. And this problem statement requires that us, you know, I think traditionally as engineers and scientists, we're trained a certain way to think of what models can and cannot do, or the questions that they can answer. So really now we're expanding outside of that box, right? So back to our chemical dosing example. In a statistical or a mechanistic mindset, if I said you need to, you know, improve chemical dosing, I would say, well, to do that, I need to understand the chemical kinetics. I need to understand the interferences with other constituents in the water. Well, in machine learning, right, we're not given any of that information, but we can predict the chemical dose, right? So it's important to be specific about your objective, but also be specific about what is your metric for success. If I can improve my prediction, right, by 10%, is that really worth deploying a data-driven model that requires a lot of maintenance when it comes to data collection and making sure all that information is good within your organization? So having a specific objective with a specific metric is one of the biggest and most important steps in the problem definition for an AI project. The next is, if I use AI, I can substantially reduce costs. Maybe, maybe not. I don't mean this in a bad way, but really what you get with AI is improved stability. Back to the dose example. Sometimes you will be dosing less than you would have originally, but sometimes you might be dosing more. And it's all about improved stability, improved robustness, and an improved awareness about what's going on within the system, right? So that's the big benefit. So long term, yes, you can save money, but if you think on the short term, you might run into some of these hurdles, for example, like labor. I mentioned all of the people that are involved in developing a data science project, especially if this is your organization's first time doing it. You're going to recognize how many labor hours need to go into understanding and deploying the project. And also, and I hate to say this, but the digital infrastructure in the majority of the water sector is kind of tailored to the 1990s, maybe early 2000s, if we talk about how data is managed and the control strategies and abilities. So as you begin to deploy your first machine learning project, you're going to learn all of the places in your organization that you can improve, and see that as your to-do list to work forward, not as a barrier to prevent you from doing more. But that should also be considered when you think of the timeline of how long it's going to take to implement your first AI project. And then finally, AI is going to replace operators. And this one really breaks my heart to hear, because AI and machine learning, if you think back to those examples that I just shared with you, those are tools in a toolbox. I also like the analogy of it. It's an ingredient in a recipe. It is not the toolbox. It is not the mechanic itself, right? Let's look at the list of, roles and responsibilities for an operator, right? AI can't do any of these on its own, right? So really what we're going to see is operations and lab and all of those folks in your organization are going to begin to grow in their scope to begin to use this new tool. And I'm especially excited for the younger operators that are really interested in getting into the data and understanding what these tools can do to be better informed about how they do their job. So with AI in the water sector, humans are always going to be in the loop. And really, it's going to be the humans that leverage and know how to use this new tool that are going to succeed in the future. So a couple of final thoughts. AI is not magic, it is math. And I know we think of, you can kind of think of AI on the hype cycle, where when it first came out, we're like, I don't quite know what it could do for me. But hopefully after this presentation and all of the other things that you hear, you are on the high end, the peak of inflated expectations. But then you go and try to deploy your first ML project and you'll run into these digital infrastructure and labor barriers that I mentioned, right? And you'll end up in the trough of disillusionment. But don't see that as the end of your journey, right? You will need to build capacity, especially if it's your first project, right? But once you build through that capacity, that is how we're going to achieve the digital utilities. It's not going to be something that happens overnight, but it is something I'm excited about seeing in the next 50 years develop in our own industry. So with that, Kyle is going to introduce some of the applications that we can use AI and ML for.
All right, thanks, Megan and Kate. So as was said, okay, there's the screen share. So as was said, my half of the webinar is going to focus on applications, but I'm going to further break that down into motivation, applications, and lessons learned. And, so first off, to zoom out a little bit, the case can be made, not to hurt any feelings, but the case can be made that the water industry, and I mean this broadly to include wastewater reuse, is relatively slow moving or slow changing. It's not like social media, where you can come out with a new app called Threads, and then within a week, you've got 100 million new US users, right? And, for another thing, a lot of our assets are literally physically set in concrete. And furthermore, we protect the public health. And so it's very well justified that any new solution to a problem should be very well proven before it's put into practice. On the flip side, though, I think the case can be made that the water industry is facing a lot of very major, world-changing challenges right now. There's climate change, there's population growth, there's population shifts, so especially high population growth in certain cities or areas, particularly the Sun Belt, and then new regulations, whether you're talking about PFAS or the lead and copper rule. We're also dealing with an aging workforce and employee retention. So just so many challenges right now, and a lot of these synergize and exacerbate each other that again, the case could be made that we're getting to a point where it's no longer change, that's the risk. It's business as usual. that's the risk. So, a way that I would like to see the water industry tackle these problems is to make better use of available data, or even to seek new sources of data. And because these tools like machine learning and other forms of artificial intelligence, like Kate described, there's a lot of different ways these can help. So for one thing, if you're talking about sort of classification style machine learning, like those early warning systems, or there's been applications where you identify pipes that are most likely to leak, pipes that are most likely to contain lead. This can move from a status quo where things are reactive, where something breaks, there's a problem, and then you go out and fix it. You can use algorithms to predict where the next failure might be, where the breaking piece of equipment might be, and then you use these algorithms to assist preventative maintenance. Another general type of benefit is going from a set it and forget it approach to treatment, where you just have these very high safety factors and just rely on those very high safety factors and a kind of fixed treatment regimen or fixed maintenance regimen, to using real-time or frequent data, and then actually responding treatment in response to that recent water quality data. And then that can then both avoid some treatment goal exceedances, but then also save cost and energy when the water quality is relatively favorable. And there's a couple reasons why I really think we are at the cusp of a lot of innovation in this space for the water industry. So for one thing, there's been a lot of innovation over the past several years on the water sensor space. So there's sensors that are available, optical sensors for UV and fluorescence. There's biological sensors like the Sentry unit, or I think ATP from the Hawk Easy series, that could be argued as like a form of biological sensor. Also even relatively frequent sensors that in the near future will be able to monitor viruses or bacteria over the interval of a couple hours. And so these are the kinds of data sources that would be needed to apply machine learning well. Not only that, but there's also a lot of innovations or better practices that people are advocating for to do a better job of data management or data hygiene within the water industry. And so I think the combination of more data and better handling of that data will really set the stage for broader and faster and better applications of AI. So again, as Kate explained, machine learning is generally said to be a subset of AI. I'm going to mainly say machine learning because most of the application examples I'm going to talk about are specifically machine learning, though some of them did involve other aspects of AI as well. And I'd like you to imagine, if you will, that we're on a tour of the water system of the future, and follow me. I'm going to give examples throughout the water cycle, from the initial reservoir management through wastewater, drinking water, and reuse. And all of these I'm going to talk about are projects that Corolla was involved on in some capacity, not always myself specifically. And most of these are R&D projects that are either ongoing or that have been recently completed. But I do feel that a lot of these, if not already being applied, could be applied in the pretty near-term future. So for one thing, Corolla's collaborated on a Water Research Foundation project number 5080 with a company called Clearwater Analytica. And what Clearwater Analytica does is they develop algorithms to forecast harmful algal blooms several days in advance. And they do this using a variety of data sources, including water quality, meteorological weather data, and even satellite imagery. So following the water from the reservoir to the drinking water treatment plant, another application that I think is really promising is modeling coagulation, flocculation, sedimentation. So right now, Corolla, specifically through our Blue Planet decision support team, is working on machine learning to predict turbidity and total organic carbon removal. We've been working on this with a couple utilities, but primarily Houston. As you can see here, we've got charts for TOC and turbidity where the black is the actual measured values and the green is the prediction. So, pretty good accurate results. All right, so now let's follow that water. It's gone through the drinking water, it's gone through the houses, now it's in the wastewater collection system. So one of the big categories of machine learning applications that Kate mentioned is early warning systems. So an example of that would be you could use it for an early warning system in the wastewater collection system or the wastewater influent if you have sensors in that, which, for the draft California direct potable reuse regulations, there's actually some text in there about requiring real-time sewer shed monitoring for direct potable reuse in California. So we did this Water Research Foundation Project 5048 with several partners, including Clean Water Services Oregon. And Clean Water Services Oregon, they did this really cool project where they took a flume of water, I believe it was grit screened primary influent, and they trialed several innovative sensors within that flume. And then they did different experiments where they would simulate industrial spills by pouring different things, either humic acid or a mixture of salt, bleach, and sodium hydroxide. And then the primary objective of that experiment was to see which of these sensors would detect those events better. But it just so happened that that also created a really excellent training and testing data set for machine learning. So we used that data set for an early warning system. And lo and behold, even though this was, I've got a really zoomed in chart just so you can see these spikes, but you zoom out, this is really noisy data because it's essentially grit screened wastewater influent, a lot of background noise. But even with that really high background noise, we were able to still detect over 60% of the data points within these events with 0 false alarms over the course of several months. So moving from the influent of the wastewater facility to the middle of it, another application that's gotten a lot of work is on wastewater control. So one specific example, this actually won a Reuse Innovation Award at the 2022 Water Reuse Association Symposium. But so we set up what we call a semi-autonomous operation system. So I wouldn't quite call it a digital twin based on the definition that Kate shared. A digital twin would be fully automated, but instead, in this case, the recommended dissolved oxygen set point was sent to an IOSite dashboard. So Yokogawa Electric Corporation, they did the back-end modeling, but IOSite did the data management as well as the dashboard in this case. And so those recommended DO set points were sent to the operators via a dashboard. They did an excellent job of actually following through, implementing those recommended DO set points over the course of business days throughout 3 weeks in September and early October. And lo and behold, there was about 10% energy savings without any compromise to water quality over the study period. But then actually, you got to be really careful with these things because it's easy to kind of cherry pick the data. But actually, in this case, there's actually more water and more influent ammonia concentrations during the days in which this semi-autonomous AI operation was implemented than in the other days in September and October. So only normalized by water and ammonia load, it looked like over 20% of energy saving per kilogram of ammonia. So another application, this is fresh off the press. So we're moving now from the wastewater to a reuse facility. So there's a Water Research Foundation project going on right now, 5129. This includes Corolla as well as Hampton Roads Sanitation District. And the focus of the project is on ozone to TOC-based ozone dosing. So there's been many studies that have found that if you dose ozone based on the TOC ratio instead of the conventional concentration times time approach, you can get a really comparable relationship between the ozone dose and the removal of different pathogens. However, a problem with the concentration times time approach is it's not really applicable at lower initial ozone doses where you cease to have a consistent ozone residual that's above the detection level of those ozone sensors. But even at that lower doses, it's still consistently shown that for a lot of viruses and a lot of chemicals of emerging concern, you can still get really good removal even at those lower ozone doses, and then just leave some of the other pathogen removal to other steps in the reuse process. The downside of that approach, however, is that TOC measures less frequently than an ozone residual sensor. So ozone residual sensor, depending on the model, they can measure anywhere from virtually continuously to about 3 minutes. TOC, it depends on the settings, but generally speaking, it takes like 15 minutes for a measurement, but also the sensors are so expensive that it's typically rotated. The same TOC instrument is rotated throughout different points in the system. So for example, at Hampton Roads Sanitation District, for the settled TOC, the TOC is only measured about 2.5 hours. So if you were to dose the ozone based on that, you'd be adjusting your ozone dose every 2.5 hours instead of every seconds, right? So it would be a slower response in the event that there were some kind of spike in the TOC or ozone demand. But we worked on a TOC soft sensor model, and we're able to get a really strong correlation between TOC and this machine learning model. And so that machine learning model could be based on more frequently measured parameters. And this would then be the compromise where you're able to combine the responsiveness, the fast response that you would get from an ozone residual based approach, while still being applicable to lower ozone doses like that ozone to TOC ratio. So moving, either further downstream in the reuse system, or maybe switching gears from a carbon-based reuse system to a RO-based reuse system. We've also been looking at a lot of membrane applications. So this was again in partnership with Yokogawa and through a different series of projects, and earlier funded by a branch of the Japanese government called METI, and more recently by the US Bureau of Reclamation. So what you see here, this is a dashboard of the semi-autonomous operations coach for the ultrafiltration. So you'll see on the left there, that's historical UF data, and then on the right, it would show the forecasted future ultrafiltration fouling. And so what Yokogawa was able to do is they were able to set this up so that you've got a machine learning based algorithm that forecasts the ultrafiltration fouling, but then it takes that a step further where the AI would then combine that fouling forecast with inputs like the cost of chlorine and so on, and create a recommended cleaning regimen, which we estimated could save about 13% of operational costs on the ultrafiltration. And that was also in partnership. This was demonstrated at the Las Virgenes Municipal Water District. So this next slide, so this is sort of a combination RO and UV AOP application. So right now, this slide is just showing kind of hypothetical dummy data just to kind of show the motivation. This is a project that's still in progress, funded by NAUI with a lot of partners, including Professor Kate Newhart in Orange County Water District. So the idea here, so right now in UV AOP for reuse, the UV dose is generally set or can be set. Sometimes if the NDMA is low relative to 1,4-dioxane, it's based on the 1,4-dioxane, but in other cases, we've got relatively high NDMA concentrations, or where you're targeting a very low goal based on the NDMA regulation. Ironically, the NDMA regulation for discharge to surface water is 0.69 nanogram per liter based on a 1 in a million cancer risk, whereas the California drinking water notification limit is 10 nanogram per liter. So depending on your initial NDMA concentration and whether this is sort of groundwater indirect potable reuse or surface water augmentation indirect potable reuse, there's often very high UV doses, well north of 1,000 millijoule per centimeter squared could be required for NDMA treatment. But there's been some studies at Orange County Water District previously where they've collected really high frequency of NDMA data. And what they found is there's actually a diurnal pattern where there's certain times of day where it's higher, certain times of day where it's lower. So in those times of day where it's lower, you're essentially wasting energy by, applying UV doses based on this, conservative, max or near max NDMA concentration. But really, a lot of the time, you can be, pretty statistically confident that the actual NDMA concentration is lower, and you really wouldn't need such a high UV dose. So the idea is if we were to create an accurate enough soft sensor for NDMA, then perhaps we could adaptively adjust the UV dose, and this would both save energy during times of lower NDMA concentration and potentially even avoid an exceedance if there is ever, a hypothetical relatively high NDMA concentration. All right, so that's it for applications. Now I'm going to talk a bit about some of the broader lessons learned and just general advice I would give. So Kate already kind of said this, but this is my own kind of spin on it. You really want a clear problem statement. So machine learning, by definition, or at least supervised machine learning by definition, it predicts, right? So you want to so you don't just say, oh, I want to optimize such and such, I want to improve such and such. You need to have a specific statement of, I'd like to predict X, right? And then once you have that problem formulation of what you'd like to predict, then you need to also think about, well, if I could predict that, how would I actually use that? What would then be optimized based on that prediction? And then, ask, do you even have data? Do you have multiple data sources that would be useful for making that prediction? And then, would a simpler tool get the job done? So, sorry to hammer you over the head with the same metaphor twice, but generally speaking, it's when you're trying to innovate, whether in data science for water or any sector, it's better to start with the problem and then try to figure out the solution, rather than to start with the solution, start with the tool, and think it's really cool and try to force fit it to a problem. Another piece of advice I would give is really establish clear and appropriate benchmarks and metrics for success. So as an example, 99% accurate sounds really good, right? But if I were to just always say, today is not Christmas, I would be right 99.7% of the time. That would be 99.7% accuracy, but that would also be completely useless. So that's an example of what's called 99% accuracy, but 0% sensitivity, where sensitivity is how often you're right when the correct answer is yes. Right, and so really, not only that, but in terms of figuring out, all right, which problem does it make sense to actually apply this to, again, you need really high sample size. So you'll want high sample size, both in terms of the number of observations, but also in terms of the number of variables, different, you want to have different data sources, because if you just got one or two data sources that you're going to make the prediction based off of, why not just do a linear model or a polynomial model? Right, but but even then, it's not just enough to have a big sample size. There's also, the quality or the range of that data. So I've got two figures here. So on the left, this looks like a really bad correlation. On the right, this looks like a really good correlation, right? Well, to quote Pam from The Office, they're the same picture. So to make these figures, I literally took the same data set that's on the right, the exact same underlying relationship, and just filtered the data down to a narrower range. So in the same way, if you're going to try to apply machine learning to a process, it's not good enough just to have a sample size of 1 million if that sample size of 1 million is all 50 milligram per liter or 0 milligram per liter. So I think it's really helpful before you start digging into the data analysis to try to maybe do some form of experiment where you vary your operational settings intentionally to make a more useful data set for modeling. So, and then the same thing applies if you're doing like a classification activity instead of a regression activity. So picture on the left, that's 15 dogs and 1 cat. Picture on the right, that's 8 dogs and 8 cats. So if you give an algorithm, thousands, million pictures of dogs and only 1 picture of a cat, and then you show it a picture of a gray cat, maybe the algorithm has only ever seen gray dogs and never seen a gray cat. So it might say, hey, this animal's gray, must be a dog, right? So it's really better to have what's called a balanced data set where you've got good sample size within each of the different categories. And then let's say you don't have any pictures of cats at all, and you've only ever seen a dog, then supervised machine learning can't help you with that at all. But other advanced data tools might. Unsupervised machine learning might say, hey, this is a really weird dog. I'm going to set off an alarm, and maybe the operator will figure out it's a cat. So another point I'd like to make, there's a lot of different strategies you can go about for applying the AI, in particular in terms of a partnership, whether you hire a data scientist to pursue it yourself, you do a university research collaboration, work with a consultant, work with a vendor such as a controls company or a data as a service startup company, and there's different pros and cons across different strategies, right? So for one thing, transparency. Are you the type of utility manager where you really want to have the right to see the code? You really want to know, is this a random forest or is this a neural net? Or do you not care? As long as, you get thoroughly proven results from an extended trial, do you not really care whether it's proprietary or not, whether it's a random forest or a neural net, right? So it's no one size fits all. It could depend on factors like you're a big utility that has the resources to bring on your own data scientists, or for your budgets, does it make more sense to kind of have a off-the-shelf solution? All right, so with that, given that I covered quite a few case studies and examples, I don't have the opportunity I don't have the time, I should say, to thank every individual who's worked on these processes, but I've got the names of the Corolla folks who are involved in these projects or in these slides, as well as the numerous organizations who have either been the test site, the funder, or the data scientists for those case studies that I mentioned. All right, so with that, I'd like to thank you all for attending, and we can go to questions.
Wow, thank you so much, Kyle, Kate, and Megan. I know I'm going to invite our speakers back on camera for the Q&A portion, and just thank you all again so much for your great presentations, your great insight into this space. And we know it's an evolving topic, so we definitely look forward to sort of hosting more conversations and webinars and sessions about this in the future. So thank you. And so I do want to remind folks, if you have questions, please do get them here in the Q&A box. And I want to dive into them and get through as many as possible. And also thank our speakers who have been typing away at some of the questions and providing written responses. So the audience can see that Q&A chat as well, should they wish to see what has been answered thus far. So I do want to start with a question about and this is for everyone to provide some input. Does the panel have any suggestions or sources looking at the application of AI to non-technical matters in the water industry? And specific examples were things like CIP prioritizing, operations budgeting, water rate setting, reducing healthcare costs as examples that were shared in this question.
I mean, I would just say, so on the CIP prioritization, I think there's been a lot of work on that space. So, as I mentioned briefly, there's been a lot of work. For example, I think American Water was doing work on, like trying to predict which service lines might be most likely to have lead. There's also been a bit on preventative maintenance on pipes for both wastewater and drinking water, and also some really cool applications on image recognition. So you send a robot with a camera down a pipe, takes pictures along the way, and then you can use photo recognition to look for cracks in the pipes. There's been a lot on that space, but on the other examples in that question, I'm not as familiar.
Yeah, unfortunately, while there are some similarities between the supervised machine learning that we described today, there are also a lot of differences. I hopped on a computer vision project last year, and that was a great learning experience. But for example, when you think about healthcare costs, you'll be collecting some very unique data sets, right? And I think you kind of run into similar problems, but it's kind of back to Kyle's question, what is the thing that you're trying to predict? And then how would you optimize or improve decision making back on that? And if you can better clarify those two problem statements, then finding resources. I mean, a lot of this is freely available. It just kind of requires you to frame your question using the right verbiage to see examples of other folks doing it. For example, the healthcare field, there's a ton of work going into how to leverage AI and machine learning, just with slightly different flavors, right, than what we do in the water sector. You know, I saw a question about air pollution control, same thing, right? It is still a predictor, just now you're in a different matrix, right, than water necessarily. So it's, especially when you're getting started, it's kind of hard to get caught up on all the verbiage to make sure that these two different problems you're seeing really may be similar predictive problems. So I wish we could be more helpful in that sphere, but unfortunately, I don't have anything I can directly point you to.
I do want to ask a question that we did receive during the registration process as well. And I'm going to kind of combine two questions in one that have to do a lot with folks that are interested in, are there any best practices, or has anyone that you're aware of, has any utility developed any kind of SOPs or guardrails around around using AI? Are there fact sheets, or is there any kind of best practices, best management type documents out there?
None come to mind for me, no, but I think that the Water Research Foundation is interested in doing some future work to develop something like that. Kyle's nodding, so.
Yeah, I would say there's, so SWAN, so the organization SWAN, they've got a guidance document more specific to like digital twin applications, but there's a document available from SWAN with kind of guidelines for digital twins. And then, as Megan mentioned, there's a recently started Water Research Foundation 5189 led by Urquidez and with co-PIs including Hazen, that's working on, you know, AI machine learning guidance, particularly with partly the angles on sort of encouraging or facilitating widespread adoption. And I would also say one of our ongoing USBR funded projects, it's a little bit early stages, but that'll be one of the deliverables for that will be a bit of an AI for reuse guidance document as well.
Thank you. And Kyle, there is a specific follow-up question on a project that you had mentioned. How do you confidently predict fouling potential in membrane filtration systems with the data that you've collected from Pure Las Virgenes demo facility?
Yeah, well, I would say so. At the time that data analysis was being run, the Pure demo facility at Las Virgenes had been running for over a year. So there was over a year of data for that particular application. Admittedly, it was really a two-part model. So there was the forecast of the UF fouling during operation, and then there was how much does that fouling then drop during the cleaning. And so that data set, you know, because you've got, loads of data points over the course of a year, depending on what frequency you download it at for the fouling during operation. But since those cleaning events were weekly, is more like a sample size of 50 plus. So the data was a little bit limited on the the improvement during cleaning aspect, and there was also a bit of an issue that there wasn't the chlorine strength for the cleaning wasn't actively measured. So there had to be sort of an assumed concentration of the chlorine for the cleaning, but in reality, chlorine solutions can weaken. So that made the predictions of the fouling change during cleaning a bit challenging. But certainly within a particular ultrafiltration run between cleanings, I think there was pretty adequate sample size and pretty confident results.
Thank you, Kyle. And I'm just doing a quick time check here for our speakers and our audience that are still here. We're almost at the top of the hour. Our speakers have so kindly are open to staying on for a couple more minutes. So we'll get through a couple more of these questions. And again, if we're not able to get to your question in the time frame we've allotted for the live portion today, please know that OCWD staff will follow up with you after the fact. Kate, I think this question might be for you. How did you decide what platform to manage databases to allow starting with those small data sets, but keeping the future in mind?
The question of database management, I will admit, is outside of my realm of expertise. So when I started working at Metro Water Recovery and we started the data handling group, our IT folks had a very, solid idea of the, database management best practices. There's a whole handbook on it called DIMBOK, and it was very geared towards, the IT side of the house, not necessarily the user side. So I think the question of which database management software to select puts a little bit of the cart before the horse. You need to understand what features you're currently missing from your existing data management strategy that you need to leverage. For example, do you have a way to access your lab data and your instrumentation data all in a single place? That can usually be a first source to kind of parse out from the data lake idea into individual data management softwares, right? I've worked with GE Prophecy. I've worked with OSI Soft Data Pi, data management, or really historian softwares in the past. And I wouldn't necessarily say that one is better than the other. It will entirely depend on what your starting point is and what your immediate objectives are. So that might be a best question for a consultant in that space.
Thank you, Kate. What measures can be put in place to make sure that the prediction does not shift away from the expected outcome when it is running on its own? I don't know if that was, if any one of our panelists would like to jump in and answer that question.
Well, I would just say that, part of the challenge of working in the real world where things change, there's water temperatures are changing with climate change. Water conservation efforts can reduce the flow, which in turn can increase the concentration of certain parameters or contaminants. So you're always, you're very likely going to have shifts in the range of the data compared to the data that you trained it on. So it is important to periodically update or retrain the algorithms on more recently collected data. But that's a challenge, right? Because particularly and if you're doing like a homegrown approach, but then your data scientist pursues employment elsewhere, then you can be a little bit high and dry, or if the vendor you were working with goes out of business. So and that's frankly a challenge of the best approach to have a model that you're able to continuously update. And honestly, because but then if you measure the thing that you're predicting, then that kind of defeats the point of the substance, right? If you do it too much, right? So maybe you can do like occasional checks, but if you're measuring the thing you're trying to predict all the time, then it's kind of, what was the point then? On the other hand, though, some of the applications that we're working on, so actually Baylor is doing some work on some of these projects where you've got the actual measurement, the prediction, and you take the difference, and then you actually set the alarm on the difference between the predicted and the actual, because then that would send a message of something really weird's going on. This system is not behaving like it normally would, and so it's kind of an unspecific alarm, but just maybe I tend to use the word alert for that kind of low level alarm of, hey, something weird's going on here. Someone should look into this.
To kind of ping off what Kyle mentioned here, I don't think that there's a single strategy that works for everyone. But what worked at Metro was for every prediction, right? Right now we're working on trying to predict pre-disinfection E. coli, right? So we have very, very sparse data collected relative to the number of predictions we're making. So we have a dashboard that this is built in OSI Soft Pi Vision, right? So it's kind of built in with their data management software, but you could equally do this in Power BI or anything that has a connection to the data historian where you have access to the model predictions. And we have a pairwise plot, right, of the prediction versus what the actual measurement is. We look at the time series versus what the actual values are. So there's a lot of qualitative checks that go into it, in addition to the real-time question of, right, what is the training or testing error in the model itself? And then, like Kyle mentioned, you can put strict thresholds of if the model makes a prediction above a certain value or below a certain value, you know, not to be feasible, then it's really easy to add in those, you know, bumpers. And I think any ML deployment, it's not going to be just strictly the model output. You're always going to have some of those bumpers incorporated in. And so that's a good way to kind of learn what works best for a specific model.
Thank you, Kyle and Kate. And if I could just ask one or two final questions just to kind of close this out. I know we're a couple minutes past, and I appreciate everyone sticking around, especially our speakers here as well. Based on your experience, what do you suggest as an effective, scalable procedure for data quality checks and data curation?
I believe Javad asked that question, who Kyle and I know very well. It depends on the type of data that you're working with, right? The data curation process of laboratory data is very different than that of instrumentation data. And so high frequency data smoothing, you know, it's one of those things that always needs to be done outside of the historian. So at that point, you're going to like a multiplicative data storage problem. And so the question is, are you really going to be utilizing this particular, you know, corrected or curated data set for anything outside of the model, or is the way that it's curated specific for the model that you're deploying? And I think some of those questions need to be answered before you can say, you know, blanket, this is how you curate the data. When it comes to laboratory data, I know a lot of LIMS systems have built in, like, are you know, a few standard deviations from the past year, right? Very small things like that, but sometimes that even won't catch, you know, someone put the period in the wrong place, or, you know, the decimal in the wrong place. Running into that with my E. coli data right now, and it's fun. So the questions of, is it going to be used outside of the model is I think your first question. And the second is, you know, with what level of fidelity do you need it? I personally just like running kernel density estimation on a lot of water quality data, because whether it's lab data or instrumentation data, you can usually capture a lot of either bimodal behavior or other shapes, right, when the distribution and catch those really extreme outliers.
Thank you, Kate. And just one final question. On average, what percentage of the time is spent on data cleansing before it can be applied to the AI model? You have an example?
Most of it.
Most of it. That's a great answer. I do just want to thank you all again. I know there's a couple questions that we'll follow up with after as well. And for our speakers, again, thank you so much. And for everyone in the audience today, if you think of something after the close of the webinar, please feel free to email info@ocwd.com with any follow-up questions or comments that you might have. And I just want to give a huge thank you again to Kyle, Kate, and Megan for your time today, and really appreciate you giving us a great overview of all the opportunities that are here now and here in the future. So we look forward again to having these conversations continued. So thank you all very much, and hope everyone has a great day.
Thank you.